So our last lecture for the dynamics unit is on uniform circular motion. And this is going to be section 3.2 from your textbook. So this is a carnival ride. Basically consists of a, it's kind of a circle, and the riders are on the edge of the circle, standing up. As the ride spins, the riders on the amusement park ride, they end up feeling that they're kind of stuck to the wall. So they're moving around in a circular motion really, really fast. And they feel this kind of push against the wall. So what is it that's causing them to kind of feel that they're stuck on the wall? So an object that moves in a circle with a constant speed is moving with uniform circular motion. And since the objects that are experiencing uniform circular motion are moving in a circular path, not only is their direction changing, but so too is their velocity. So that would imply that they're accelerating. So consider it this way. If we have a, remember we went back to one of our first lectures, we talked about the straight line distance between 2 points. And if that straight line distance is changing in direction, then an acceleration is occurring. But the line itself is the same size. So what we're having here is an acceleration, and even if we are moving at a constant velocity in a circular motion, because we're changing our direction, we have an acceleration. So what is it that causes the feeling that you're stuck against the wall? Well, anytime we have an acceleration, we have to have a force, because F equals ma. So that's the force that we feel. And we'll get to that soon. It's the centripetal force. But how do we find this acceleration? Well, looking at, this is an image of a circle here. We have P and Q, 2 points that are labeled on the circle. P would be our first point, Q is our second point. Our velocity 1 and our velocity 2 have the same magnitude, but their directions are different. So that's something that to keep in mind. Now, there is an angle between the two. So our R1 and our R2 are equal, but the angle between them, it varies. So if we take that triangle, the OPQ triangle, and below you see a triangle with labels of delta V, V2, and V1, what we'd end up having is our delta V is the difference between V2 and V1, but because these are congruent triangles, and because the values are the same, what we end up with is a magnitude that's equal to v squared. And our we would have to divide by the radius, and because R1 and R2 are the same, that radius would be r. So our centripetal acceleration can be found as v squared over r. And this goes through it a little bit more in depth. So since v1 and v2 are perpendicular to the radii of the circle, the acceleration vector points directly toward the center of the circle. And acceleration is directed toward the center of the circular path is called centripetal acceleration. Now when we write a centripetal acceleration, if you're asked to solve something, normally you wouldn't write the direction because when you have that AC, it's implied that the direction is towards the center of the circle that the motion is occurring around. So here's a slide to copy down. Uniform circular motion. It occurs when an object moves in a circle and its speed is constant. Since direction changes, the object experiences centripetal acceleration. So it's AC equals v squared over r. That's going to be on your formula sheet. Now, centripetal acceleration is always directed toward the center of the circle. That's why we do not write typically what the direction is after we solve for a centripetal acceleration. So let's look at a simple little problem here. We have a child on a carousel, and the radius of this carousel is 5.1 meters, and it rotates with a constant speed of 2.2. So if we have to calculate the magnitude of the centripetal acceleration, that's going to be 2.2 squared and we have to just divide that by our 5.1. We end up with 0.949. We had two digits, significant digits in the question, so we have to round to significant digits. That gets us to 0.95. So sometimes you may not know the speed of an object moving with uniform circular motion. However, you may be able to measure the time it takes for the object to move around the circle. The time it takes for something to move around a circle or to go through a cycle is the period. If you have something that's moving really quickly, sometimes we talk about how many revolutions it has per unit of time, or revolutions per second, or hertz. That's the frequency. Now, what you would remember from your previous science courses, f, the frequency, is equal to 1 over the period. So frequency and period have a reciprocal relationship. We can substitute these into the centripetal acceleration equation, and we'll end up with this formula here. AC equals 4 pi squared r over t squared, or AC equals 4 pi squared r f squared. Now this is on your formula sheet, but I would recommend copying it down just so that you're aware of what, how do you use this equation and what each variable means. So let's look at this problem. We have a salad spinner, and it says here that the salad spinner has a radius of 9.7 centimeters. It rotates clockwise with a frequency of 12 hertz. And we're asked to find out what's the what at this specific instant is the magnitude and direction of the centripetal acceleration of lettuce at that point in time. Now this one is a little bit different because they are specifically saying a point when the lettuce is moving to the west. So we will have a direction in our answer. If it doesn't specify which direction we're moving or where we're taking our centripetal acceleration initially, then we usually do not include the direction. So in order to do something like this, what we're going to do, we're going to take our, look at our equation, AC equals 4 pi r f squared. I'm using this equation because I was given frequency. So I wasn't given a velocity. So just substituting in 4 pi, I believe pi is squared in this. Yep, 4 pi squared. R is going to be in centimeters, so we have to change that to meters. That was 0.097. Our f is 12 squared. And calculating this gets us to times 0.097 times 12 squared. This gets us to 551.43. Now looking back at the problem, looking back at the problem, what we see is we have 9.7 and 12 are the two values given. So because the only values given have two significant digits, we take our answer and we record it as only two significant digits. So when I finally write this down, I'm going to put 550 meters per second squared. Now I was going to the west initially, so my answer for this one would be going to the north. So another problem, centripetal acceleration at the end of a fan blade is 1,750 meters per second squared, so that's the acceleration. The distance between the tip of the fan blade and the center is 12 centimeters. So calculate the frequency and the period rotation of the fan. So let's look at this here. So we know AC equals V squared over R equals 4 pi squared R F squared. We're going to find the frequency first. And in this case, our AC is given to us. And we need to find our F. So let's rearrange this for F. So F is going to equal AC over I guess F squared is going to equal AC over 4 pi squared R. So F is going to be the square root of AC, and then I can find the square root of these, 2 pi and the square root of R. So all together, my F is equal to the square root of 1750, and the other number is 12 centimeters. So over 2 pi and the square root of 0.12. So if I calculate this, 1750, I'm going to get the square root of that, divide that by 2, and pi and 0.12. I end up with 19.2, I guess 20, and then I can, after round, looking back at the question, it says 1750 and 12.0. So let me just show that. The 1750 implies that there are 3 significant digits. The 12.0, because we're showing that 0.0, that implies 3 significant digits as well. So that means that our answer, we're going to have to have 3 significant digits, which is going to be 19.2 hertz. And then to find out what our period is, our period equals 1 over the frequency, and that's going to be 1 over 19.220. I have to use the exact value, so a lot of calculators have this reciprocal button, so I'm going to hit that, and I get 0.0520 seconds after recording 4 significant digits. So I have this answer and that answer. So according to Newton's laws of motion, an object will only accelerate if a force is exerted on it. And since an object moving with uniform circular motion is always accelerating, there must always be a force exerted on it. This is why what I was saying earlier, even though the v is constant, we do have a change in direction, which means we have an acceleration. And anytime we have an acceleration, we have an F, a force, because F equals ma. So the force that we have is called the centripetal force. That's the force that causes the centripetal acceleration. It's always directed towards the center of the circle. Without that force, the objects would not be able to move in a circular path. So using Newton's second law and AC equals v squared over r, we can find that Fc is equal to mv squared over r. And this is a slide to copy down here. This gives us our relationship between Fc and mv squared and r, and it also gives the relationship when we have period and frequency. A centripetal force can be supplied by any type of force. So when we have the Earth-Moon system, the centripetal force is the force of gravity between the Moon and the Earth. That is causing that that circular motion. A car moving around an embankment has a frictional force that's directed towards the center of the circle. That would be causing that circular motion. If you're spinning a ball around in a circle, the uniform circular motion that you'd experience there, or the circular motion you'd experience, the centripetal force there would be the force of tension of the string. So here's an example. If we have an astronaut up in space, so we're trying to eliminate gravitational forces, they're spinning around a ball on a yo-yo. They're spinning around a yo-yo, and the force of tension is causing that centripetal force. The velocity vector of the yo-yo will always be perpendicular to the force, the centripetal force. So if we can cut that string, what happens is the yo-yo ends up moving on the last velocity vector on which it was aligned. So it'll move in a straight line, and it'll obey Newton's first law in that way. So let's look at a problem here. This is interesting because if we're looking at choosing a type of material to make an embankment for a car to drive around, the friction of that material is important. So here we have a car that's moving around an embankment. It weighs 2,200 kilograms. The radius of curvature of the road is 52 meters. The coefficient of friction is 0.7. What is the maximum speed the car can make the curve without skidding off the road? So let's switch to our paper here. And our givens are m equals 2200 kilograms. Our radius is 52 meters. Our mu is 0.70. And I believe that was it. So now we have to find out what's the maximum speed the car can travel. So we are looking at AC equals v squared over r. And we're actually looking at the force in this case. So let's look at FC equals m v squared over r. So if we're going to not be moving, our FC has to equal our FF. So let's make this equal to our FF. So our FF is mg times mu. So making this equal to that, we end up with mv squared over r equals mu mg. Our m's divide out, so we're left with v equals the square root of mu g r. And we can solve this. Square root of 0.7, 9.8, and r, which is 52. So 0.7 times 9.8 times 52. And we find the square root of that. We end up with 18.88. And we have to report this as 19 meters per second because we had two significant digits up here. This was two significant digits, two significant digits, and two significant digits. So what we saw in that last problem was that in order to prevent our car from falling off the road, we had to, or we set FC equal to FF. So the centripetal force was equal to the frictional force. And that basically gave us our limit for the speed that we can travel. Another way that we can kind of increase that speed that somebody can travel before their car starts to slip is with banked curves. So what we see here, a lot of roads are designed this way where you have to make a kind of turn on a highway or onto an expressway. There's a banked curve, so the car is moving, is not on level road, but they're on an angle. And you can see that the normal force of the car can be split up into components, the Fn sine theta and Fn cosine theta. What would then happen is that we not only have just the friction force and the centripetal force, but we also have a portion of the normal force contributing in keeping our car on the road as well. So if we have this arrangement, the formula is tan theta equals v squared over rg. That's the relationship between them all. So we get the tan theta because that when we rearrange this, we'd end up with an Fn sine theta and Fn cos theta, and then we'll have a sine over cosine. When we isolate that, we get tan theta equals v squared over rg. I'm not going to go through that right now just because I don't want to make these lectures too long. But you have that formula on your formula sheet, and you will be able to use that to solve some banked curve problems. This also happens in other situations. For example, an airplane that's tilting to make a turn, the angle of the tilt can be used to calculate using the tan theta equals v squared over rg equation. It can be used to calculate the centripetal force. Another interesting aspect of uniform circular motion, because uniform circular motion involves a centripetal force Fc, we could hypothetically have artificial gravity in a space station if the space station rotates at such a velocity that the AC generated is 9.8 meters per second squared. That would simulate Earth gravity. So what this would look like, if you look at the next slide here, we have people walking on this space station. It's a circular space station, and as it's rotating, there is an Fc that's causing the rotation. That's centripetal force. That centripetal force causes an AC, and the AC is, if we can make that equivalent to 9.8 meters per second squared, then you could essentially treat your Fc as a normal force. So the centripetal force would be like a normal force. So if you've seen some science fiction movies, Interstellar, for example, or Space Odyssey, 2001: A Space Odyssey, they have rotating space stations. They're kind of using this concept in physics. So that's the last lecture for this unit. Keep posted on the course website, and I will be letting you know what to study for the final unit test.